Good morning, everybody. Let's wait the canonical 5 minutes before we resume the lecture. So I will mute myself, and we'll see you in 5. Okay, folks, it's 9:05. We'll let people join as they come. Once again, good morning, good afternoon, or good evening, depending on where you're located on the globe. So continuing with our discussion, so yesterday we began our discussion of so-called coupled chemical reactions, meaning how do chemical reactions that are coupled to the electron transfer event affect or modify the response that we observe. As we mentioned, in this context, we use 2 letters, C, referring to a chemical step. We use E to refer to an electron transfer step to convey the particular mechanism. We mentioned, for example, that a CE mechanism, also referred to as pre-kinetics, involves a previous chemical reaction. For example, it can be an equilibrium, and this equilibrium is then responsible for the generation of the redox active species OX. It can then on to carry out the electrochemical reaction. So it's called pre-kinetics because a chemical step precedes the electron transfer. In a similar vein, we can talk about post-kinetics, meaning a reaction that follows the electron transfer event. And so now we call it EC because we have electron transfer first, chemical reaction afterwards. And so this would be, as depicted here in blue, OX plus N electrons goes to red, and then in turn with a red constant KF goes to Z. Z can be or not be redox active. More often than not, it's not active, but we will consider a mechanism where it is in fact active in a couple of minutes here. A variant of EC is EC catalytic, sometimes referred to as EC prime. And what that means, so you see here, OX plus electron going to red, similar to what we had above, but now red reacts with substrate to generate a product and recycle OX. And so in this context, red plus S is basically the catalytic process. It regenerates OX, which goes back to the electrode surface. And in the process, you make P, which is the product. And then an ECE process, so you have 2 electron transfer events, and in the middle, you have a chemical reaction. So as depicted here, you have OX plus N electrons at E0 prime 1. Goes to red. Red can be converted to Y, which in turn is redox active with N2 number of electrons at a different potential, giving rise to Z. And there are 2 cases of an ECE type mechanism depending on the values of E0 prime 1 and E0 prime 2. Mainly is the order in which they come. So for example, if we look at this case, if we're sweeping the potential, right, we first encounter E0 prime, as shown on, here and on top. When red converts into Y, the second redox process, E0 prime, is well before the E0 prime 1, meaning that there's a large overpotential for the second electron to go in. And so one can assume that the moment you generate any Y, it rapidly gets converted to Z. On the other hand, if E0 prime 2 is more, let's say, negative than E0 prime 1, then we can go from OX to red, red to Y, but in order to go to Z, we need to scan the potential further to the right. And as we'll see later on, these are very, very different profiles in terms of the voltammetric response. Now, a couple of things to keep in mind. One, you might recall very early on, we talked about the transit time. That is the time it takes to traverse the thickness of the Nernst diffusion layer, delta. We guesstimated that as delta squared divided by 2D. Remember that we could solve for gamma, the Nernst diffusion layer thickness, as 1.61 d to the 1/3 omega to the 1/6, meaning the faster we rotate the electrode, basically we compress the Nernst diffusion layer. And so we can vary the thickness of delta, we can vary the thickness of delta here by varying the rate of rotation. And the idea is to compare the transit time, how long does it take to leave the Nernst diffusion layer versus T1/2 for the reaction. Meaning, if the transit time is very short and the T1/2 is long, then we'll basically be insensitive to that reaction because it takes place on a time frame where it doesn't really affect the voltammetric profile. On the other hand, if TD is long and T1/2 is short, then we'll be extremely sensitive to that because a reaction takes place while the species are within the Nernst diffusion layer thickness. And so it says in coupled chemical reactions, we need to look at the relative rates of the chemical reaction versus the transit time, which is basically what we just mentioned here. And the transit time to make it through a Nernst diffusion layer, basically this character here. And now, since delta is controlled by the rate of rotation, then we need to look at how the observed response varies on the rate of rotation. But remember, when we were talking about changes in the voltammetric profile as a function of rate of rotation, we mentioned that in order to eliminate the dependency of the current on the rotation rate, remember from Fick's law, the current, for a simple process, remember that current will be proportional to omega to the 1/2, right? And so in order to look at changes in the shape of the response, then we must normalize the current to the rate of rotation as we did before. And so therefore, what we will really plot is the current normalized to the square root of the rate of rotation versus potential as a function of omega. And in this case, we'll be looking at changes in the wave shape, having factored out any dependency of the current on the rate of rotation. And so we begin with pre-kinetic CE process. Remember, we mentioned that what this involves, so X here is what you put in the beaker. And then there can be a pre-equilibration or a protonation or Leon loss, some chemical step that converts X into OX, which is the redox active component. And so the chemical step, this pre-equilibrium, will determine how much OX is present. And so one can immediately see that the normalized current will be a function of omega. Why is that? Because as we vary the rate of rotation, what we're doing is increasing the flux, but that flux can only keep track with the rate of rotation when the chemical reaction, this pre-equilibration, is fast enough. If it is not, what we will observe in a qualitative sense is as we go to higher and higher rates of rotation, the normalized current will decrease. And so what are the some of the limiting cases here? It says if T1/2 is much shorter than TD, meaning at low or small omega. What is it that we're doing? We're giving the reaction a lot of time to take place so that if the conversion of X to OX is rapid relative to the transit time, then the normalized current will be proportional to the concentration of both X and OX, right? Because in essence, and so remember, this pre-equilibrium then partitions your reactant into X and OX, which is redox-active. And so if that conversion is very fast relative to the transit time, meaning low omega and or fast K forward, then the current that you observe will be proportional to the sum of the concentration of both X and OX. If, on the other hand, T1/2 is much longer than T sub D, then it's essentially as though X was not in solution. In essence, whatever fraction of X was converted to OX in that pre-equilibration, then the current will only be proportional to that concentration. And so the limiting case at high omega is that the current will be proportional only to the concentration of OX, as opposed to the concentration of both OX and X. And so, and then of course, if you have intermediate values of omega, then you have intermediate values of that normalized current. And so at the low omega limit in blue, in here we have that the current is proportional to both X and OX. At the high omega limit, the current is proportional only to the concentration of OX. And then at intermediate values of omega, you see intermediate values of the normalized current. Notice that we are normalizing the current to the square root of the rate of rotation. If there was no dependency at all of those lines would fall on the same profile. Now, if we want to determine the value of the chemical kinetics, one way which we can do this is plot the normalized current as a function of, sort of a broad function of omega, typically log of omega. And what is it that we would expect? And so we know that at low omega, we have large limiting current, basically this guy. At high omega, we have a lower process, mainly this guy. And so as we go from low to high, we see a transition from essentially a constant normalized current, this transient behavior down into another plateau. From the dependency of the normalized current to the omega, we can actually at least guesstimate what the value of Kf is, basically by fitting the data to these profiles. If we had a faster reaction, then it means that we need to go to faster omega to basically beat it to the punch. And so by looking at how the normalized current varies as a function of a broad function here of omega, so you have a broad range of omega values, you can generate working curves for the mechanism in place and basically just fit as a function of Kf, and then you can guesstimate at least a reasonable estimate of, in essence, what is the value of these guys here. Something to keep in mind that the detectability of pre-kinetics is a function of the product of K forward and the equilibrium constant not just Kf. For example, if you have a large value of the equilibrium constant K, then Kf has to be small, since if both K and K forward are large, then in effect, all of the material is present as ox, right? What we're saying, if this equilibrium constant is large for this conversion here, if that has a large value of the equilibrium constant and Kf is fast, then basically, so for example, if K is 100 and K forward is fast, then 99% of X is converted to ox, will basically be no effect. And so in the case where K is large, Kf has to be small. And that's the idea where it's being able to detect pre-kinetics is a function of the product of both K forward and the equilibrium constant. If the equilibrium constant is small, K, then Kf can be large or small, because then there's only a fraction of the material has been converted to ox. And so these are things that we need to keep in mind when we're trying to employ this approach to look at coupled chemical reactions where we have a preceding chemical step before the electron transfer event. So that was pre-kinetics. What about post-kinetic or EC processes? As we mentioned earlier, in this case, what we have is a reaction Kf that follows the electron transfer and thus post-kinetics. And so the first question is, does this affect the mass transport of ox? And the answer is no, because ox doesn't know and doesn't care that this exists. It'll be transported to the electrode surface as if there was no other reaction taking place. And so the first thing to keep in mind is that the limiting current, the normalized limiting current, will not change, right? Because ox is not being affected. What will change? Well, if we are consuming red in this reaction, then the ratio of ox to red will change, meaning red will be at a concentration that's lower than would be dictated by the potential because it's being consumed in this K forward step. What are the consequences of that? If we are changing the ox to red ratio, if we go to the appropriate Nernst equation, E equals 0.59 over n log red over ox, if the concentration of red is lower than it should be, then we're subtracting a smaller number than we should. What does that mean? That means that the voltammetric profile will be shifted on the potential axis while the normalized limiting current will stay constant. Okay, and so it says here, since the ratio of ox to red will decrease, then the wave will be displaced on the potential axis. And how will it be displaced? If we're subtracting a smaller number, that means that the wave will be displaced to less negative potentials. And so this would be for EC post-kinetics. At high omega, we see the red profile. In the limit of low omega, where a lot of this reaction takes place, there's a dramatic shift in the location of that voltammetric profile. But notice that all of the profiles, all of the profiles normalized to the square of the rate of rotation reach the same value as it should, because we are not affecting the transport of ox to the electrode surface. And again, by looking at the displacement of E1/2 as a function of omega, we can actually extract the value of Kf. What about EC catalytic? In this case, we assume that the concentration of substrate is much larger than the concentration of ox, so that we're actually looking at the kinetics of that catalytic step. Mainly, just to refresh our memory, in this process, we reduce ox to red. Red reacts with substrate to generate product and regenerates ox. So there are a lot of moving parts here. So how can we think about this? The first is that there is an EC process, right? And we just saw that for an EC process, as the kinetics kick in, that wave will be shifted on the potential axis. So we would expect some shifting of the potential of the voltammetric profile on the potential axis as a function of omega. On the other hand, if we look mechanistically what's happening here, we are regenerating ox that goes back to the electrode surface. So we in fact have a higher flux of ox at the interface because of this regenerative step. If we are affecting the effective concentration of ox so that its transport is affected, that means that the normalized current will also change. And so we have, in essence, a combination of EC and CE processes. We can think this is clearly EC process, but then the second one would be basically CE, since it affects the regeneration of ox, which then again goes back to the electrode surface. And so one way to think about this, so if we go in general, as it should be evident by now, what we do is consider the two limiting cases of very high omega and very low omega. And so in the high omega limit, we are rotating fast enough that basically this reaction is precluded. It doesn't happen. And so we'll see a voltammetric profile at the potential corresponding to that process. In addition, the limiting current here, this, will be proportional to the number of electrons in that first step. As the catalytic reaction kicks in, we are consuming red, and therefore the wave should shift to less positive potentials. But in addition, we are regenerating ox, so we increase the flux of ox to the electrode surface. And so in the low omega limit, we should observe a wave that is shifted on the potential axis, but also we have a larger limiting current due to the catalytic step. And then clearly at intermediate values of omega, we see a transition in terms of both the limiting current as well as the displacement on the potential axis. One very peculiar dependency is if we look at a Levitz plot, meaning I versus omega to the 1/2, at low values of omega, the EC catalytic current will be higher than the diffusion one, which is unusual, but that comes from the fact that we are regenerating ox, we're increasing the flux. And so it's the only mechanism that will have that. And so this is extremely diagnostic of an EC catalytic process. Now we have sort of a rhetorical question, right? If I look at these profiles, one needs to, again, keep in mind that at the low omega limit will be limited by the kinetics. At the high omega limit will be basically, there will be no contribution to the either the limiting current nor the displacement on the potential axis. So next on the agenda is ECE processes. So remember, in an ECE, we have two electron transfers separated by a chemical reaction. So here we have ox going to red. That's the first E. Red goes to Y, and Y in turn goes to Z, which is the second E. So this is E. So we have E, C, E. Now, in this case, the first electron transfer is negative of the second. And so, as we mentioned earlier, if once we generate red, when it reacts to give you Y, at that potential, at these potentials, right? Y, it has enormous overpotential to be reduced to Z. So any Y that we generate here will be immediately reduced to Z. And so again, how do we think about what the profiles will be at high and low omega limits? Again, at high omega, we basically outrun the chemical reaction. So all we see is ox plus one electron going to red. In the red here, the limiting current proportional to N1, right, of electrons. In the low omega limit, we give this reaction plenty of time to take place because there's a CEC process, and then we regenerate, not regenerate, but we produce Y, which is redox active. So the wave will be displaced, and the limiting current will also increase. Now, you might ask yourself, isn't that what we just saw in EC catalytic? Right? Doesn't this look awfully similar to that? If you're saying no, you're not paying attention, right? So the question here, how can we distinguish such a mechanism from an EC catalytic? And the question, the answer to that depends on how fast this process is versus how many electrons are transferred here. In discrete electrochemical processes as shown here, N might be 1 or 2 in that ballpark. And so the limiting current here, the limiting current is proportional to N1 plus N2. So this might be twice the size of the first one. On rare cases, maybe 3 times. In this case, however, if we have a very fast turnover of red with the substrate, the limiting current here can be 100 times N. And so by looking at the relative magnitudes of the normalized current at high and low omega, we can actually discern how many electrons were transferred and distinguish between an EC catalytic and an ECE process, as mentioned here. Okay. Now remember that we also have the second variant of an ECE, where the second electron is negative of the first. And so how do we understand this process? Again, our sort of canonical go to high omega limit and low omega limit. In the high omega limit, we basically outrun the red to white conversion. So we don't make any, or at least in the time frame for the transit time, it's basically undetectable. And so we would see a profile like shown in the red line here. If we then let the ECE process kick in, right, then if we go back here, if that's the case, then red is being consumed. And so as in any EC process, that wave will be shifted on the potential axis. But also we are generating some Y. And so if we scan across the potential region where Y is active, we should see an increase in the current. And so in the limit of low omega, we see a displacement of the wave, as you should expect from the EC type process. And we also see the emergence of a second wave, because now we're reducing Y to Z. This limiting current will be proportional to N1. This limiting current will be proportional to N2. And notice that the profiles look very, very, very different. This looks enormously different from that. And that's because the order of the reactions makes an enormous difference in terms of the voltammetric response. Okay. Now, these are the more common or the most common coupled chemical reaction mechanisms. You can get a lot more complicated. And when we discuss cyclic voltammetry, we can indulge in things a little bit more complicated. But in general, this will cover the vast majority of the systems that you're likely to encounter. An interesting twist in all of these is that very often in these reactions, especially when you're dealing with organic transformations, if you're doing this in aqueous media, then the pH can have an enormous effect. And so then you have to sort of consider, you know, in a parallel fashion, what are the consequences of changing the pH in the environment in terms of if it's a protonation, for example, if it's fast or slow, what is the pK of that reaction? And so it can get a little bit more involved, but if you understand the fundamentals on how to look at these processes, then you should be able to unravel even rather complex mechanistic pathways. Now, next we consider our RDE, which stands for rotating ring disc electrodes. And so let's do that again. This is, I have to give thanks for the animation to Dr. Chihao Lee in my group. I don't know how long it took him to make this, but I'm happy that he did. And so in a ring disc experiment, right? And this idea of Saturn, because you have sort of concentric circles here. If you look at this in a little bit more detail, in a ring disc electrode, this is a rather complex electrode system where you have two electrodes whose potentials and currents you can control independent, or measurements you can do independent of each other. On the right, so here is an actual picture of one of these rotating disc electrode systems. If you're ever going to buy one, buy them from Pine, as I mentioned before. They are the best, period. One of these, let's say, if you get a platinum, disc and platinum ring electrode, that'll probably set you back about $2,500. And you might say, that's a lot of money for an electrode. Trust me, it's worth it. So how does this work? So we have a disk in the center. So here is the disk. We can talk about the radius of the disk R1. And then there's a gap between the first electrode, which is the disk, and the blue electrode here, which is the ring. And so R2 minus R1 is basically the gap between the two electrodes. For a well-designed and machined electrode, this should be of the order of 20 microns. And typically what is done, if you have a cylinder as the disk electrode, you put a sleeve of things like heat shrink Teflon, and then you put the ring. This is a very complicated process. And as I mentioned earlier, let the professionals do it. The ring then has a radius of R3 minus R2. The point here is now that you can control the potentials of both the disk and the ring independently, and you can measure the currents of the ring and the disk independently. And so it gives you an enormous advantage for looking at coupled chemical reactions, because now you're sensitive to the products of the reaction by monitoring the current at the ring. One of the most common types of experiments in a ring disk electrode is a so-called collection experiment, meaning I generate something at the disk and I collect it at the ring. So here's what the flow profiles look like. These types of experiments are often referred to as reversal technique. Why is that? Because at the disk, we have aux going to red. At the ring, we can have the reverse process, red going to aux. And so at the ring, we'll reverse what we did at the disk in the simplest of cases. And so what we see, if you look at the flow lines here, so aux gets turned into red. There is the gap here, some transit time here associated with that. And then at the ring, we can basically reverse the process. So what does the profile look like? How do we plot data in this context? And so the idea is to plot both the disk and the ring currents on the same plot. And so, for example, here we have this current. The current here is proportional to the reduction of aux to red. This is at the disk. So here ID tells you that's a disk current at this potential. It's the limiting current at the disk. At the bottom, you can plot the ring current. This is the limiting one. But more often than not, you will see on that profile a little arrow that tells you where the ring potential is poised. And so clearly, if this is a potential of the ring and we're scanning the potential of the disk, the moment we start making some red, so basically this corresponds to aux going to red, the moment we make any red, it gets swept to the ring, and we can detect it at the ring by going from red to aux. Now, the ratio of the ring limiting current to the disk limiting current is called the collection efficiency. There is a theoretical collection efficiency that's dictated exclusively by the geometry of your specific electrode. By that, I mean, what is the value of R1, R2, and R3? And there is a very complicated formula that you can calculate that. However, you really need very precise measurements of R1, R2, and R3. And for example, if your gap is 20 microns, that's going to be very hard to measure experimentally. You're not going to be able to put a pair of calipers in there and measure that. A much easier way is to calibrate your ring disk system. How do you do that? you choose a system that you know is chemically reversible. For example, if you look at ferrocene oxidation to ferrocenium, if this goes at the disk, then at the ring, ferrocenium, you can oxidize back, reduce back to ferrocene at the ring. Both of these species are chemically stable, and so you can measure that collection efficiency. The collection efficiency for a well-designed electrode might be of the order of about 0.35 or roughly 35%, meaning you recapture about 35% of the stuff you generate at the disk, you capture it at the ring. And you might say, that doesn't sound, too good a collection efficiency. In fact, it is, because you have to remember, if you look at these profiles, only the species that are very close to here will make it across to the ring. So there's a lot of diffusion of species. Remember, there's a huge concentration gradient for red, which is not present in solution. And so you lose red because of diffusion, because of transport, etc. And so the best way to carry out an experiment is to experimentally measure the collection efficiency or the theoretical or maximum collection efficiency for your specific electrode. Once you do that, that number is independent of the rate of rotation, because it's a fraction of whatever you make at the disk that you're detecting at the ring. So why is something like this useful? So it says, in the case of systems without kinetic complications, meaning everything is stable, the collection efficiency will not be a function of omega because nothing is happening. However, if you have coupled chemical reactions, especially EC, meaning red is being consumed, then L will be a function, and in some cases, a very strong function of omega. And so if we have ox plus any electrons going to red, red going to Y. So this is EC as we have seen it before, right? With a forward rate constant KF, and if you want, a half-life of T1/2. If there were no EC process, then let's say we get something like the red profile here. Notice that, again, we're pointing to where the ring is. If there's an EC type process, we will see that the ring current will decrease, it will be lower than for the case of no EC, because we're basically consuming some of the red that would otherwise be redox active at the ring. And this ratio of ID to IL will change as the rate of rotation changes. And so in order to investigate these type of processes, what we'll typically do is monitor the effective collection efficiency or the experimentally measured collection efficiency as a function of omega. And we want to get some profiles that might look something like this. And so at low omega in this regime, we can see that we have a very low value of the collection efficiency, meaning most of this stuff is reacting, and so it's not making it to the ring, and so therefore the ring current is very low. Remember, N is the ratio of ring to disk current. As we start rotating a little bit faster, we begin to be competitive with those kinetics. And so now our collection efficiency goes up. Eventually, it will reach the theoretical limit, which is the dashed line. So I'm showing here two lines, a blue and a red. So let's have a quick vote here. You can vote in the chat. Tell me which one is faster, 1 or 2. I'll give you a minute for you to vote, and then we can decide. So vote for your favorite, 1 or 2. And we have no votes yet. Or maybe people are not paying attention. And let's see. Anonymous attendee. 1, 1, 2, 1, 2. Already. Chat is disabled. Sorry. No, chat should be in the questions and answers. Sorry. And 1, 2, but I'm not sure. 1, 2. There's a. Okay. So let's think about this. What we're plotting here is how fast do we need to go to outcompete the reaction, right? And so in the case of blue, we have to rotate roughly at that velocity. Here, we have to rotate this. So reaction 2 is clearly much faster since we have to rotate faster to beat it to the punch. So the correct answer is 2. And I'm sure now everybody's going to say 2. Okay. And so this is a kind of analysis that hopefully will become a little bit clearer in your minds, because now you understand the physical processes involved in here. And notice why, we put so much emphasis on transport, because transport is intimately related to all of the electrochemical responses that we observe. That's what we, had, significant discussion of transport, be it by diffusion, be it by convection, be it by electrical migration. Now, some practical aspects of voltammetry. Electrode materials, lots of usual suspects here. Probably the most used electrodes are typically platinum, gold, and carbon. Platinum and gold because they are inert as metals. Carbon because it's very good, particularly for organic materials and also for inorganic ones. Depending on what you're interested in finding, you can use electrode materials that simply serve as an electron source or sink. Or if you're looking at the behavior of the electrode itself. So for example, one can think of either polycrystalline or single crystal electrodes. As we mentioned when we were talking about absorption, surface sites have an enormous difference. And so if you look at all of these materials, fortunately, they're all FCC metals. And so one can distinguish between, let's say, a 111, 100, or 110. And so the reactivity of that interface to various molecules, for example, oxygen reduction or CO oxidation, etc., can be extremely electrode surface geometry sensitive. In recent times, copper has also become a popular electrode material, mainly for CO2 reduction. So there's now an emerging body of work using copper as single crystals, nanoparticles, oriented nanoparticles, etc. Carbon, as I mentioned, is also a very common material. Glassy carbon is a really beautiful electrode material. Glassy carbon, also known as vitreous carbon, is a very hard substance made by the pyrolysis of typically things like It has high conductivity. It has a very broad potential range. Paralytic graphite, think of this as a graphite block. The advantage of something like this is that you can mount it and then peel layers and have expose a clean layer every time you peel it with things like, Scotch tape, to be precise. Paralytic graphite, because it's a layered material, one can distinguish between the so-called basal plane or the edge plane. And those can have enormously different reactivity. So you really have to know whether it's on the basal plane that will look like basically an extended aromatic or graphene-like. On the edges, it's going to be like a layer structure. More frequent ones, graphene and other 2D materials like hexagonal boron nitride, molybdenum disulfide, etc. There's a lot of interest in these things, in that they're novel materials. They have very peculiar band structures. You can also, for example, in the case of graphene, you can actually do electrochemistry on a single layer of graphene, which is almost a perverse type of an electrode. We've done some work in that area. You can also, because it's very flat, and if you play it right, you can have essentially a perfect single layer. You can look at diffusional dynamics on these things. So the question is, how do radioactive species diffuse in 2 dimensions on something like graphene? If we have time, we can talk about that later in the course. But a lot of emphasis these days on 2D materials. I also mentioned mercury and mercury film. This is more historical. People these days try to stay away from mercury because of toxicity concerns. But mercury is very good for trace metal analysis. In particular, mercury films are still used. What you do is you start with a very dilute solution of mercury, let's say of the order of 1 micromolar. And then you can deposit a mercury film in the solution where you also have trace metals. This will basically, the trace metals will dissolve into this film. So you pre-concentrate the metals into the mercury film, and then in so-called stripping, you go to positive potentials, and you basically strip them off from that film. You can get enormous sensitivity on these things and limits of detection of the order of, less than picomolar, which is really quite remarkable given the relatively inexpensive instrumentation. What about electrolyte? Remember, an electrolyte is a combination of a solvent and a salt that's dissolved and dissociated. We can have either aqueous or non-aqueous systems. In aqueous media, the potential window is pH dependent, because you get into hydrogen evolution or oxygen evolution, depending on whether you're going to positive or negative polarizations. However, the window itself will be 1.23 volts, because that's dictated by thermodynamics. You can extend this window by using electrodes that have lousy hydrogen evolution or oxygen evolution kinetics. For example, carbon is not particularly good at either, so you can extend the range of potentials in aqueous media that you can study. There is also, you can do a trick that basically takes into account a lowering of the activity of water. If you go to very highly concentrated solutions, the activity of water decreases dramatically. And because remember, even though we said that we almost never know what that value is, so we'll assume that concentration equals activity. When you go to solutions like 10 molar or 15 molar KCl, the activity of water drops like a rocket. And you can actually do electrochemistry in like a 2-volt window, which is really dramatic. That's being exploited these days to make aqueous batteries that are safe, but that can sustain a higher voltage that would be otherwise impossible in aqueous media. Non-aqueous solvents, perhaps the most widely studied, are acetonitrile and methylene chloride or dichloromethane. You have to make sure that they're dry. Acetonitrile is notoriously difficult to dry because if you use a strong reducing agent, you reduce the CN into an amine, and then you get a mess. At least in my experience, the best way to make dry acetonitrile is to distill it from calcium hydride. So distill from calcium hydride or reflux it from calcium hydride, which is a strong enough reducing agent to reduce any oxygen and water that you have, but not strong enough to reduce the nitrile group in acetonitrile. Dichloromethane can be also readily dried. One of the issues with dichloromethane is that it has a relatively low dielectric constant, so you have to be cognizant of ohmic drops or IR drops in your system. Acetonitrile has a dielectric of about 35 or something like that, so it's a little less sensitive to that. Dimethylformamide has a very extensive negative potential. It can go beyond 2 volts. Dimethyl sulfoxide has a very good positive limit, around 2 volts or so. THF, tetrahydrofuran, has a very extensive window of stability, but it has a very low dielectric. This is about 4. And so getting electrolytes to dissolve and dissociate can be very tricky. You can use things like tetrahexyl ammonium perchlorate. So perchlorate salts are typically used in non-aqueous solvents. And so, for example, as mentioned here, tetraalkyl ammoniums, where you can have a tetrahexyl ammonium BF4 or PF6, that's soluble enough in THF to make it accessible as an electrochemical solvent. Propylene carbonate is very popular in battery applications, particularly for metal oxides. And you can have either propylene carbonate or other carbonates like methyl carbonate, ethyl carbonate, dimethyl carbonate, and a mix of all of those. So carbonates are generally used because they have a good positive potential limit where the cathode materials in batteries will be active. Dimethoxyethane and other quote-unquote glymes, these are basically polyethers. Similar to THF, they have a relatively low dielectric constant, but they also they're a little bit less volatile. So, you know, one of the issues with THF is if you bubble nitrogen or argon to eliminate oxygen, then you're really evaporating THF. And so if that's what you're trying to do, a very, nice trick is to pre-saturate your stream of either nitrogen or argon in THF. So you bubble it through a little round bottom flask that has THF, then use that stream to degas your cell. And in so doing, the stream is already saturated in THF, so you don't evaporate it from your cell. Non-aqueous electrolytes, tetraalkyl ammonium perchlorates are common. Tetraalkyl ammonium BF6 and PF4. Typical methyl, ethyl, butyl, and hexyl will be the typical ones. Lithium TFSI is used a lot in battery materials. and there's many more, that one can use. Let's take a 5-minute break because we're now going to change from hydrodynamic transport to diffusional mass transport. So according to the official chronometer, it's 10:03. Let's reconvene at 10:08. We'll see you in 5 minutes. Okay, folks, let's start again. Let me get a bit of peace. For those of you who are wondering, that is actually tea with honey, not a gin and tonic. So up to this point, we've been considering hydrodynamic transport for the rotating disk and ring disk experiments. We are now going to change the mode of mass transport from hydrodynamic to diffusional. And we start with chronoamperometry, which, as the word would suggest, it's a measurement of current versus time. Contrary to the case where we have hydrodynamic transport, the current is now going to be a function of time. Remember, when we were talking about RDE, we said that those were steady state responses, independent of time. Now, on the other hand, we're going to have transient measurements that hopefully will of value in terms of looking at kinetics. And so we begin with chronoamperometry, which as I say is a technique based on diffusional mass transport. Experimentally, you can think of it the following way. So in blue here, we have a typical voltammetric profile. So at t equals 0, we're at this potential. At t bigger than 0, we put a potential step that goes into the mass transport limited region. Okay, that's the experiment that we're doing. And the question is, how do we describe the response? How do we understand what those transients tell us, and how can we take advantage of those responses? So here we use fixed laws of diffusion. The first one you've seen previously tells you that the current is equal to the number of electron transfer, Faraday is constant, error of the electrode, diffusion coefficient, and basically the gradient, the concentration gradient of X at the electrode surface as a function of distance and time. The second one basically tells you what the gradient is in terms of the diffusion coefficient and the second derivative with respect to distance. And so how do we go about doing this? And so, I mean, we'll do this in a very generic way, not with any detail, but basically, whoops. We need to solve fixed laws with the appropriate initial and boundary conditions. These are partial differential equations. And so the way we do this is using Laplace transforms, which we will just give you what the answers are rather than going through the whole process. I remember the very first time I taught electrochemistry, I was an assistant professor at University of Puerto Rico, and I did the entire derivation, which is, I mean, it's doable and relatively straightforward, but you quickly realize that it's a colossal waste of time because students within a picosecond will forget how the derivation was. And so we're not going to do that here, but rather provide you with what the conditions are and basically go straight to what Laplace enables us to do. Remember, the benefit of Laplace transforms is that it enables you to take partial differential equations, make them into algebraic equations. You can solve them in the Laplace plane and then back transfer to sort of called the real plane. And so that makes life a lot easier to solve these types of equations. And so what are the initial and boundary conditions? Remember, when you have differential equations, you need to state initial and boundary conditions appropriate to the particular situation that you find itself. And so initial conditions, it says that the concentration of Ox as a function of distance and time. So X is distance and 0 here is time. So it's X and T. It says that at t equals 0, the concentration of ox, regardless of position, basically at any x, is basically the bulk concentration of ox. This is referred to as the homogeneous solution condition, meaning if you take any sample of solution from your cell, it all has the same concentration. There are no concentration gradients anywhere. The solution is homogeneous. Second condition, so we have Cox of infinity and T, meaning that at any time, T, right, it's the variable there, if you go far enough from the electrode surface, infinity in this context would be, I don't know, 100 microns, thereabouts, so you're beyond the nearest diffusion layer thickness, you're back to the bulk concentration of ox. This is a so-called semi-infinite linear diffusion condition. And it basically means if you go far enough away from the electrode, the solution doesn't know that there's an electrode out there, right? And that's the semi-infinite linear diffusion condition, something that is very common to a lot of techniques in electrochemistry that have diffusional mass transport as a mode of mass transport. And then the third condition depends on the specific experiment that you're using. So for chronoamperometry, it says that the concentration of ox at the surface, x is 0, as a function of t equals 0 for t bigger than 0. Meaning, if we go back, it tells you that this is at t equals 0, this is t greater than 0. Remember, we're at the transport limited regime. We have complete concentration polarization, so the surface concentration of ox is 0. And that's what basically that means. And so if we start and apply the Laplace transfers to fixed laws of diffusion, we get the following expression, that the concentration of ox as a function of distance and time equals the bulk concentration times error function of x, which is distance, diffusion coefficient, and time. And so what does this provide you? It tells us, so the concentration of ox as a function of x and time, x and t. X is distance and t is time. So those are basically the concentration profiles, how the concentration of ox varies with distance x and time t. And it tells you how that varies as a function of time. Everything else here is a constant, right? And so this expression tells you how the concentration distance profiles evolve as a function of time. And you get something like this. So here we're plotting surface versus bulk concentration. It goes from 0 to 1. At time equals 0, that ratio has to be equal to 1 because we're assuming a homogeneous solution, right? For t greater than 0, remember what we're doing is stepping into the transport limited regime. So the concentration at the surface drops to 0 basically instantaneously. Now you have this enormous gradient that is propagating into the solution. So this, if you think of this as 1, 2, 3, and 4, these are 4 different times. At the shortest times, because you're forcing the surface concentration of ox to go to 0 at the surface, you have a very steep profile. As time goes on, this profile diffuses into the bulk solution, and you can see the slope gets shallower, meaning the concentration gradient decreases. If we go back, so that's basically, we just solved for that guy, right? If we go back to fixed first law of diffusion, it tells us that the current is proportional to that gradient. And so inherently, we know, we haven't said so yet, but as time increases, the current will go down. It will start high and it will decrease. So intuitively, we have some idea as to how these things should work out. And so then from fixed first law, which is what we just looked at, right? This is basically the flux or the gradient. We just saw what the error function was. We can then get what the gradient as a function of distance and time are. And this is just simple math here. We're not going to dwell into the details here. We're just going to look at what the end results are. If look at x equals 0, that is at the electrode surface, right? So if we go to x equals 0, what do we get? Notice that this conveniently drops off. So we end up that partial c partial x equals bulk concentration, square root of pi, square root of the diffusion coefficient, t to the 1/2. Right? And so we just solved for this, right? That's what that is. So if we substitute this into here, we get this, which is called the Cottrell equation. And it tells us that the current is a function of, as usual, the number of electrons, Faraday constant, area of the electrode, bulk concentration, square root of the diffusion coefficient, the geometric factor, and the square root of time. Meaning the current in a potential step chronoamperometric experiment will scale as 1 over the square root of time. It will decrease with increasing time, which basically we could have told from the variations in the slopes of these profiles. Notice also the scale here. This is microns. Okay? This is basically the propagation of the Nernst diffusion layer into solution. And so if we put all of this together in a more visual fashion, so here's the experiment, right? E initial, E final into the mass transport limited regime. What do we observe experimentally? We see very steep rising current that decreases as basically 1 over t to the 1/2. And so given that this is the scaling, if we make a plot of current versus 1 over the square root of time, that should give you a linear profile that basically goes through the origin. If you have deviations from that, it indicates coupled chemical reactions. And so our criterion for mass transport control is that the current should be proportional to 1 over the square root of time. It's unfortunate that it's 51, that's the page number, so let's just erase that. So it's not the 51st root of that. It's the current proportional to 1 over the square root of time. That is our criterion for mass transport control. If we recall, when we were talking about RDE, right, from the Levitch equation, we mentioned that our criterion for mass transport control is that the current was proportional to the square root of the rate of rotation. Is there any similarity between that and that? And please say yes. And what is that? Omega is what? Let's say radians per second. We're taking the square root of that. So basically, this whole thing to the 1/2 power. That's basically the same scaling as square root of time. And so the larger message here is that any technique that is based on diffusional mass transport will have a 1 over square root of time dependency in it, or square root of time, just generically. Why is that? If you look at the diffusion expression, right? This on the side here, x equals 2 root dt. X displacement, diffusion coefficient time. And because in diffusional mass transport, basically things are diffusing in or away from the electrode surface, distance, right, which is that displacement, is proportional to the square root of time. And that dependency will be reflected in any and every electrochemical technique that you can imagine. And thus in rotating this, because remember, at the interface in the Nernst layer, it's diffusional mass transport. In here, by definition, it's diffusional mass transport. So we will see this dependency on the square root of time, something that will come up time and again. What about coupled chemical reactions? And so it says here, although the theory for applying potential step chronoamperometry to coupled chemical reactions has been developed, it is not used often for such purposes. The reason is that there are easier ways to do that. Okay? We just saw RDE, and when we talk about cyclic voltammetry, we will do that as well. There is one exception. And that exception is in the study of ECE processes. In particular, when you have the second electron easier than the first, which was the first ECE type process that we discussed when talking about rotating this electrode voltammetry. Remember that in this case, X goes to red, red goes to Y, Y goes to Z in a second electron transfer step. If we look at what the response would be, this is what which is a little bit involved, but it's really, I mean, if you think about it, this is the Cottrell equation where we have taken out the number of electron transfer. So we have this Cottrell factor multiplied by this term that takes into account the number of electrons and basically the conversion, KFT, basically the conversion of Y to Z. Right? Because here you have K forward. And so the rate at which Y is converted, that basically reflects this contribution. And you can immediately see that if at long times you have e to the minus big number, which is basically 0, So at long times, the current will be proportional to N1 plus N2. At shorter times, it's going to be N1 plus maybe a fraction of N2. And how does that come about, in the plots that you would make? Remember that we make a Cottrell plot is current versus 1 over the square root of time. So if we do that here, so current versus 1 over the square root of time. Here we have the experimental plot, which is this curve. But if we extend the linear portion, so you have that's a linear section and that's a linear section, the slopes of those two sections will be proportional to the number of electrons transferred. At longer times, right, proportional. Remember, longer times 1 over, because it's a reciprocal, it's short on the scale. The slope is proportional to N1 plus N2, because basically this term is going to 0. At shorter time, mainly higher on this profile, the slope will be proportional to N1. And so the experimentally observed profile, this red line, nothing else, and I mean nothing else, looks like that. And so it is extremely diagnostic of an ECE process. Again, because of the being sort of the flavor of the week these days, this type of analysis has been resurrected in the study of CO2 reduction to multiple carbon products. And that's because you have a cascade of electron transfer events. If you do a potential step measurement, it will be extremely sensitive to that. And so you can have, in some cases, more than 3 linear sections, depending on the time resolution of your experiment. And so, as I mentioned, even though potential step chronoamperometry is not often used for coupled chemical reactions, the ECE under this condition is probably the one exception where it's extremely valuable and powerful. Now, a variant of chronoamperometry is called Chronocoulometry, which is really just a mathematical transform, right? So in Chronocoulometry, we measure charge versus time, not current. But it's basically the same experiment. That is, we do a potential step from an initial potential to a final potential. We already know what the response to that will be, basically the Faraday current, which is given by the Cottrell equation. If we integrate the current, right, the integral of current is charge, so charge equals the integral of I dt. We basically integrate this with respect to time, right? Because we have t to the 1/2 here, a 2 comes up, you can see it here. All of these other factors stay there, and basically pi t to the 1/2 comes up. And so this expression tells you that the charge equals 2 NFA, bulk concentration, diffusion coefficient, square root of time divided by pi to the 1/2. This is just a simple integration of the Cottrell equation. If we look at a profile like this, then this would suggest that we should plot Q versus square root of time. If we do that, we get something like shown in here. The first thing to notice is that it does not go through the origin, right? Why is that? Because you have our pesky double layer charge. And so doing experiments of this sort is a convenient, quick, and dirty way of calculating or guesstimating what your double layer charge is in an experiment. Actually, in reality, what you have is this term, right, that comes from this guy, plus double layer charge, plus if you have adsorption. And so in the presence of adsorption, that intercept will be displaced on the q-axis by an amount that will correspond to the adsorbed charge. And so chronocoulometry is used extensively for estimating double layer charging and adsorption processes at electrode surfaces. Now, there is a variant in both chronoamperometry and chronocoulometry. And that is, if you recall, when we were looking at rotating discs, we had this ring disc that represented a quote-unquote reversal technique, because at the ring, we reverse what we did at the disc. So we have the opportunity to do that here a little bit easier in terms of the experimental setup. You just basically step back to the initial potential, right? So before in chronoamperometry, right, we would put a potential step. Now what we're going to do after some time delta, we go back. And so now this will be referred to as double potential step chronoamperometry or double potential step chronocoulometry. And so this describes the techniques. In the red here, that will be straight or simple chronoamperometry. We then go back after some delay time tau to the initial or some other potential. It doesn't have to be the initial, but frequently it is. If we think of it in terms of a voltammetric profile, we start here, we step into the top of the wave, and after some time t, we go back to the initial one. What are the responses? So the forward response is what it should be because we haven't changed anything. The electrode doesn't know that we're going to yank it back after the initial step, right? And so for the forward step, the responses are the same as we saw before, basically Cottrell equation and the integral of the Cottrell equation. Again, this is a page number. However, at time tau, we step back and we see a transient, both in the current and charge profiles. So how do we describe these processes? And so for the reverse step, we have, again, what's basically this comes from the Cottrell equation. And now we have an expression that takes into account time. And in essence, this t minus tau, think of it as a reset in your measurement. Meaning, we went from ox to red, we waited, and then had a second potential step. So this t minus tau is like the zero set for the reverse step. And that's what that basically, that's what that comes about. For the charge, again, this comes from the integration of the Cottrell equation. And you basically integrate this guy, and you end up t1/2 minus t minus tau to the 1/2 power. And so in this case, you would plot the forward response using these expressions, the reverse response using these expressions for the current or the charge, depending on what you're looking at. What would something like this be good for? Well, more than anything else, looking at EC processes, because this is a reversal technique. And so if the green profile is in the absence, so this is no EC. When EC kicks in the dashed blue, you capture less of the material at the electrode surface. This is equivalent to the collection efficiency in ring disc experiments, and it's basically conceptually very similar. And so by following how much of that current you recapture on the reverse step as a function of tau, you can actually get reasonably good kinetics for this process. The analogous thing here in terms of charge, so here the dashed line would be for a straight integral of the charge. The green would be with no EC, and the blue is when you have an EC process. Why is the profile lower? Because remember, what we're doing here, what we're plotting is charge, right? Which means that if you have an EC, you have less charge on the reverse step than if there was no EC process. These types of experiments became very popular when computers became essentially pervasive in electrochemical laboratories. These types of developments had their heyday in the late 70s, early 80s, when computers really came into the lab. Now, the use of chronocoulometry is particularly useful for adsorption, right? Remember that we were very sensitive, right, from these types of plots. If both ox and red are adsorbed, one can estimate what the double layer charge is by taking steps between a potential at the foot of the wave and a potential beyond the adsorption wave. Assuming that the double layer capacitance is not a function of potential, which, for let's say narrow delta E, that's a reasonable approximation, then we can derive the following expression. That is Q, which is double layer plus adsorbate, equals area of the electrode, capacitance, which we're assuming to be minimally potential dependent, difference in potentials here, and this NFA gamma 0. Remember, this is the surface coverage, area of the electrofarad constant sin m. And so a plot of Q versus E1 minus EF can be used to determine C double layer and gamma 0. And so in essence, what we have here, so it's like we had before in terms of a double potential step. So we go, from the forward step, we wait tau and come back. In this case, however, rather than measuring the current, we're measuring the charge. And as we saw before, for the forward and reverse, for the forward step, Q versus T1 half, right? Because that's what we were told that we should do, right? Q versus, T1 half will give us, Q versus square root of time here. And then for the reverse versus T1 half. If we look at the difference between intercepts, That difference can tell us basically how much stuff we have, how much of we have absorbed on the electrode surface. And so for T bigger than tau, that is on the second part of the potential step, you plot this. This is generically known as an Anson plot. Remember when we talked about adsorption, we mentioned Fred Anson, a giant of electrochemistry who was at Caltech for many years. He has been emeritus now for a while. This is called an Anson plot, and it's extremely convenient for measuring the charge associated with adsorbed species on an electrode surface. These things are so pervasive that almost all potential stats these days, in their menu for techniques, there will be one so-called Anson plot. So you know what that means now. It's very valuable and it's very easy to implement, and it has reasonably good accuracy in terms of measurements of surface coverages. Now, a different technique here, in all of the ones so far, we've been talking about holding the potential constant. That is chronoamperometry. A variant of that is called chronopotentiometry. It's a galvanostatic, meaning we control the current. So we impose a constant current and monitor the potential. Thus, chronopotentiometry, because we're measuring the potential as a function of time. How does this work? For the excitation, right? Notice that this is current. At t equals 0, we impose a current. Translation, we impose a rate. Remember that current in this context is synonymous with rate. And we monitor the potential. And a typical profile, if we look at the potential versus time response, is as shown here. So this is where we put the current step. We'll see a profile that looks normally like that. If we extrapolate this, this is called the quote-unquote transition time, tau. And the transition time occurs when you basically reach complete concentration polarization, meaning the surface concentration of ox goes to 0. And you might ask, why does it have that shape, right? In essence, you impose a current step. So now you're converting ox to red. The moment you run out of ox, you're still imposing a current. And so the potential will drift until it finds another redox couple that it can basically sustain the current density that you're imposing, and thus the very sharp increase in potential. So how do we develop the theory for this? Because we're imposing a constant current, we will have a constant gradient because Mr. Fick tells us that we have to. Right? So if this is the bulk concentration of ox in the beginning, when we impose a current density, all of these profiles will have the same slope. They have to, because we are forcing it to be that way. The profile will propagate into solution for sure, but the slope will be the same because we're forcing it to be constant, right? Remember, from Fick's law carries number of electrons, Faraday constants, area, diffusion coefficients. All of these are constant. So it tells you that the current is proportional to that guy. If this is constant, then this has to be constant. And these concentrations, distant profiles as a function of time will be parallel to each other, and the slope will depend only on the current density that you are imposing on the electrode surface. As we did in the case of chronoamperometry, we use Laplace transforms to solve for Fick's law, but we now have different initial and boundary conditions. Some of them are the same, one in particular is not. So we start, as we had in chronoamperometry, the concentration of ox at any distance at time zero is the bulk concentration. Again, we assume that the solution is initially homogeneous. There is no gradient anywhere in there. The second condition, if you go far away enough from the electrode surface to infinity, the concentration of ox is again the bulk concentration of ox. This is what we have referred to as semi-infinite linear diffusion condition. And it's called semi-infinite linear diffusion. Basically, if you think of the electrode, you're looking normal to that surface. So it's one linear diffusion to that interface, semi-infinite, because we assume that in direction away from the electrode surface, that's infinitely long. And infinitely long means, more than, 200 microns. The third condition is very different from what we had in chronoamperometry, right? If we go back to chronoamperometry, the condition was that for t greater than 0, the surface concentration of ox went to 0, right? In this case now, the boundary condition is that for t greater than 0 at the surface, we have a constant gradient dictated by the current. When you basically solve for all of this, you end up with the so-called sand equation, which tells you that I versus t to the 1/2 equals number of electrons, Faraday constant, area of the electrode, diffusion coefficient, square root of pi, concentration divided by 2. Okay. Notice that everything here is either known or constant. So if we examine the sand equation, as we just mentioned, IT to the 1/2 is constant because all of the terms here are constant or known, right? Again, number of electrons has a constant. Faraday constant better be a constant. Area of the electron, diffusion coefficient, pi and c. The criterion for diffusion control is that IT to the 1/2 be constant, meaning if I change the current density, the product of the current density times the square root of the transition time is a constant. Meaning, if I change the current density, right? If I make this, let's say, bigger, the transition time will adjust so that the product of I tau to the 1/2 is constant. And that is the criterion for diffusion control. This will be the case. So IT to the 1/2, I tau, should say, will be constant for reversible and irreversible charge transfer, as well as EC. It will not be constant for CE or ECE, Why? Because the transport of species is affected, and thus IT to the 1/2 will cease to be constant. I tau to the 1/2 is known as the chronopotentiometric constant for good reason. Very often it's expressed in this fashion to basically normalize for area of the electrode and bulk concentration. And so it makes it easier to compare different systems. So what do chronopotentiometric waves look like? Right? Again, we begin with a known quantity, Nernst equation. E equals E0 prime, 0.059 over n, log concentration of X, concentration of R at the surface of the electrode as a function of time. We can solve and substitute for the concentration terms, right? So Cox equals bulk minus this term. C red, because it's not initially present in solution, is given by this. After substituting and grouping terms on the Nernst equation, we get the following expression. That E equals E0 prime, 0.059 over n, log square root ratio of the diffusion coefficient of X and red, plus 0.059 over n, log tau to the 1/2 minus t to the 1/2, t to the 1/2. Does this look familiar? Well, I mean, you might recall our voltammetric expression, right? That it was E equals E0 plus, log ratio of X and red, and I limiting minus I over I, right? This looks awfully similar to that. When t time equals 1/4 of the transition time, what do we have? Tau to the 1/2 minus t to the this should be 1/2, not over 12, sorry. This should be 1/2, and this should be 1/2. When that's the case, we have basically log of 1, which goes to 0. And so we end up that E equals E0 and this term. This is referred to as a quote-unquote quarter wave potential because it takes place at a quarter of the transition time. And this is essentially analogous and virtually identical to the voltammetric E1/2. Remember, in the E1/2 is when the current was half the limiting current. This term basically went to 0 because that ratio was 1, so log of 1 equals 0, and then we had E equals E1/2. Now we have E equals E1/4 because it's a condition, the potential at 1/4 of the transition time. To look at reversibility of a system, much like we did in voltammetry. Remember, in voltammetry, we plot E versus the log I limiting minus I over I. Now we have E versus log tau to the 1/2 minus t to the 1/2. Again, these are 1/2s, sorry. And for a reversible reaction, the plot will be linear, surprise, surprise, with a slope of 59 over n millivolts. And this is a criterion for reversibility. As we've seen now ad nauseum, for an irreversible reaction, the slope will be 59 over alpha n millivolts, assuming, if alpha is 0.5, then basically the slope here, this will be 180 millivolts as opposed to 59 millivolts. An interesting thing here is when you have multiple electron systems. Let's say you have two 1 electron steps. If you do the math, you end up that the ratio between tau 1 and tau 2, basically for N1 equal N2, let's say 1 electron transfer, the second transition times is 3 times the first one. Meaning something like that. So this is 3 times that guy. And just basically falls out of the math. There's nothing magical here. Now, a better question is, why do chronopotentiograms look the way they do? And by the way, for those of you involved in battery research, this sure as hell looks like a discharge profile in a battery, right? Where the current density, think of it as the effective C rate that you're applying to your battery. What if I plot it like that instead, right? So notice all I did is rotate it. Here's E right there. And this is potential over here. Does that look familiar? Right? Does a profile that looks like this look familiar? Where this might be pH and this might be volume. It looks like a titration curve, right? And in fact, if you look at the math, right, this is from freshman chemistry, the so-called Henderson-Hasselblad equation, right? pH equals pK log ratio of basic form, acid form. Here we have E equals E0 prime, 0.059 log ox red. And so mathematically, it's identical. And so that's why chronopotentiograms look like that, because it's basically an upside down titration curve. The math is essentially the same. And so you see, you know, as in a titration curve, right? The pH initially doesn't change very much, and all of a sudden it takes a jump. Here, the potential stays more or less the same and then jumps. Because here you basically have the ratio of oxide rate controlling the potential. When you run out of one of them, then you really jump. You can think of this as the equivalence point when you're charging or discharging, the same way that this would be the equivalence point in a titration where you have a dramatic shift or jump in pH. And so hopefully you see it now, okay? Again, we're at the top of the hour. Let's take 5 minutes and we'll go on to lecture set number 3. So we'll see you in 5. And we are back, folks. So now we start with our discussion of what is often people's favorite, linear sweep voltammetry and cyclic voltammetry. Just give me a second. So experimentally, what you do is you scan the potential, typically in a linear fashion, you measure the current. In linear sweep voltammetry, it's a single sweep. Cyclic voltammetry, basically a triangular wave, and you get, the canonical. Let's see if we can get that back. No. Cyclic voltammetric profile, often referred to as the ducts. Okay. The first thing is that the name is a misnomer. This is not voltammetry, right? We're neither rotating the electrode nor stirring the solution. The technical name, the appropriate name would be linear potential sweep chronoamperometry, right? Because we're measuring current as a function of time. But nobody calls it that. We will call it cyclic voltammetry because the term is so ingrained that it would be foolish to do otherwise. In fact, the original publication that describes the theory of this, if you ever search by cyclic voltammetry, you would never find it, because the title of the paper is Theory of Stationary Electrode Polarography. And we'll get to that in a couple of minutes. So let's not get ahead of ourselves. So how does cyclic voltammetry work? So here is the profile that we showed before, right? So here is that profile, right? And now what we're doing is looking at different points on that profile and looking at what the concentration distance gradient is as a function of potential, but remembering that embedded in that is also time. And so because you have the convolution of potential and time, the response here is a little bit more complicated, but we'll get to that in a second. When we're looking at these profiles, right? So if you go to A, right, we're so far removed from any region of electrochemical activity. Here we're plotting surface versus bulk concentration goes from 0 to 1. At potential A, there's essentially no change. It's just flat out. We're back to homogeneous solution condition. At B, we're beginning to see a little bit of current, a little bit more at C, and at D, right here, D, we reach complete concentration polarization. We have the steepest slope because Mr. Fick tells us that it has to be that way, right? The highest current is the highest partial C, partial X that is equal to 0. The steepest gradient at that interface. Then at potential E and potential F, you'll notice that even though everything, basically we're still complete concentration polarization, the slopes are decreasing, and we will eventually also get back to the bulk concentration, the condition of semi-infinite linear diffusion. And just by looking at how these profiles change and how those slopes change, we can tell the current goes up and then comes down, as we see right here. Again, notice the length scale here is in microns. So how do we understand the theory of this technique? So for Ox going to red with only X in solution, we're once again back to Fick's laws, right? Because we have diffusional mass transport. And so in this case, we use the following initial conditions. The first one is the same we've had all along, right? That at time equals 0, independent of the distance, right? The surface concentration of Ox is the bulk concentration of Ox. And once again, we have a homogeneous solution starting off. A boundary condition that we've also seen before, at infinite distance, let's say 100 microns or so, at any time, we're back to bulk concentration, the condition of semi-infinite linear diffusion. But then the boundary condition gets a little bit more involved. Remember that in the case of chronoamperometry, the boundary condition was that for T greater than 0, the surface concentration went to 0. And that's what we ended up with Cottrell equation. In the case of chronopotentiometry, the boundary condition that for time bigger than 0, we imposed a constant current, therefore a constant rate, therefore a constant concentration distance profile as a function of time. In this case, the boundary condition is a little bit more involved. And it basically relates to the ratio of oxide red at the electrode surface, x equals 0, as a function of time. And what we have is that it's an exponential, NF over RT, initial potential, V is sweep rate, and E0 prime is the formal potential of the process. And so this, in some sense, it's like taking Nernst's equation and folding it into how do we determine the ratio of oxide red, starting from an initial potential value, how rapidly we move that potential relative to the potential at which there is electrochemical activity. Because of the way this boundary condition works, it does not have a closed solution. So you have to solve it numerically. The net result is what's shown in here. Tells you that I equals NFA square root of the diffusion coefficient, bulk concentration A to the 1/2, where A is sweep rate, V NF over RT. And then this term here is basically the current function. It's a numerical function. And that's why this equation has to be solved numerically, not explicitly. It doesn't have a closed solution. And so here we come with the first people to do this. Theory of stationary electropolarization, right? 1964, almost 60 years ago. Nicholson and Shane from Department of Chemistry, University of Wisconsin. Shane actually then ended up being the provost at the university. There's a big building named after him. And so look at the name, Theory of Stationary Electropolarization. For those of you who are not familiar, polarography is an electrochemical technique that involves a so-called dropping mercury electrode. So I think, as we alluded yesterday, a dropping mercury electrode is an electrode where you have a capillary that has a huge reservoir of mercury on top. The capillary typically of the order of like 20 to 30 microns, and the pressure of the mercury on the capillary forces droplets of mercury to form, and then when they get too heavy, drop. Thus the term dropping mercury electrode. And so when it says theory of stationary electropolarization, that's basically double negative. The electrode, in polarography is not stationary, right? It's a dropping. So when you say stationary, it goes against that, and it's not polarography either. But the official name of what we refer to as cyclic voltammetry is theory of stationary electropolarization. This is probably the most cited and least read paper in the history of electrochemistry. Later today, I will send you a PDF. At least pretend to look at it so you can claim that you have at least seen it. It is a monumental piece of work. It is just rigorous beyond description. incredibly informative, with providing enormous insights. So if we go back and look at this current function, so basically it says a current function for a reversal charge transfer. And so you can see here's the current function. It tells you the value of the current function as a function of the potential, meaning how far you are from E1/2 or the formal potential. And you can start way far away from that potential, 120 millivolts. The current function is essentially 0. As you get closer and closer, this current function gets bigger and bigger. And when you're at minus 28.5 millivolts from E1/2, that current function has a maximum value of 0.4463. This is an arbitrary number. It just happens to be the maximum of that function. Okay? And so, as we just saw, for an electrochemically reversible system, this chi of AT, this current function, has a maximum value 0.4463, as you just saw right here. And so therefore we have the peak current 0.4463 and FA bulk concentration D0 to 1/2 and F over T square root of that square root of V. If we take values of the constants at 25 degrees C, one obtains the following expression, that IP is 2.69 times 10 to the 5th, n to the 3/2. Notice that, n to the 3/2, area of the electrode, bulk concentration, square root of the diffusion coefficient, square root of the sweep rate. This is the so-called Randall-Sevcik equation. It is a fundamental equation of cyclic voltammetry. Okay? Notice the dependencies or the scaling. The peak current scales as n to the 3/2. Not n. Area of the electrode, bulk concentration, square root of the diffusion coefficient, square root of V, basically in volts per second. The peak potential basically comes from the peak current, right? So when you take this was the maximum in the current function, so it relates the peak potential to the E1/2 and this Nernst factor. For an electrochemically irreversible system, we have a similar expression, except that now we have a different current function or numerical function. And now B takes into account alpha and n sub A, basically the number of electrons transferred in the rate determining step, alpha being the transfer coefficient. If we do the analogous analysis, this function x of bt has a maximum value of 0.4958. And so we can substitute in, and we get that in this case, IP equals 2.99. I don't know why they still do this, but in the literature they do that. I would have called it 3 and be done with it, but no. And alpha NA, meaning transfer coefficient, the number of electrons transferred in the rate determining step. This would be the total number. Area of the electrode, bulk concentration, square root of diffusion coefficient, square root of the sweep rate. If we compare a system that, or two systems that exchange one electron, we compare the responses for a reversible versus irreversible case. If we assume in the irreversible case that alpha equals 0.5, then the ratio of peak currents for the irreversible to the reversible will be 0.78. meaning the peak current for an electrochemically irreversible process is 78% of the value of an equivalent reversible process. In this case, let me go back to one. Something I forgot to mention, in the Ransel-Sevcik equation, this expression gives you the E1/2, the peak potential that is independent of the sweep rate, right? It's just 1.019 RT over NF. And this will be the same, not a function of sweep rate. And I mentioned that because now, in the case of an irreversible process, the E peak is sweep rate dependent, right? And E peak will be displaced or will vary with V at the rate of about 30 over alpha NA millivolts per decade change in sweep rate. Again, if we assume that N sub A is 1 and alpha equals 0.5, this will be displaced at a rate of about 60 millivolts per decade change in sweep rate. So if we look at a reversible versus irreversible process, so here we have the reversible process, normalized current 1, irreversible 0.78, and also there's a displacement in the potentials from the reversible to the irreversible, delta E. Okay. And that delta E will be a function of sweep rate. Again, you might recall when we were talking about current over potential for systems that were fast, slower, and really sluggish. These displacements are basically a reflection of that, right? So you can think of that versus that, which is basically no different than that. And that's exactly where they come from. If you do a reverse sweep, then the current, you can look at the current in the forward and reverse sweeps. Let's say in the forward, ox being reduced to red, the reverse red being oxidized back to ox. We can talk about the difference in peak potentials, 59 over N millivolts, and for a reversible process that is independent of the sweep rate. We can also estimate the formal potential, E0 prime, as essentially the average of the two values of the E peak potential, E peak anodic and E peak cathodic. The current proportional to square root of time, this comes from basically the current is proportional to the square root of sweep rate, right? You might recall our earlier discussion when we said whenever you have a process that is diffusion control, there will be a square root of time somewhere in there, right? V, the sweep rate, is basically volts per second. You take the square root of that, there's your square root of time dependency. Measuring currents can be a little bit tricky. And so, for example, if you extend the background like that, and here's assuming that if you're far from the point of zero charge, you're basically charging a double capacitor, which is linear in potential for small excursions, then this would be I pick cathodic for the reductive process. The reverse is a little trickier because you're extending this profile. And so that would be the anodic reaction. For a process that is chemically reversible, meaning both ox and red are chemically stable entities in the time frame of your sweep, then I peak anodic over I peak cathodic should be equal to 1. The potential at which you switch the direction of the sweep can have an effect on the voltammetric profile. You have to be far enough from the peak potential to ensure that the surface basically has a concentration of a reduced species that corresponds to the equal bulk concentration of the oxidized one. And that typically is of the order of maybe a little bit over 90 millivolts. If you were to reverse a sweep, let's say at this potential, the profile would not look like what we have here. And so in this cyclic voltammetric profile, things, the typical experimental measurables that people will always quote. Certainly, what is the formal potential? And that is specific to any particular chemical system. And it's reasonable enough to take it as the average of EP cathodic and EP anodic. If the ratio of peak currents equals 1, we can assume that the system is chemically reversible, meaning both ox and red are chemically stable entities in the time frame of your experiment. Electrochemical reversibility, meaning that the system is always in equilibrium with the applied potential, that is a delta E peak of 59 over n millivolts and is not sweep rate dependent. It's actually 58.5, but let's just call it 59. For a system that is diffusion controlled, the peak current will scale as the square root of the sweep rate. And so our metric for mass transport control is that if you make a plot of I versus square root of sweep rate, this would be linear. And from the slope, you can actually get the diffusion coefficient. There are different ways in which one can analyze irreversible systems. One of the easiest one was a process developed by Nicholson. That's the same Nicholson as in Nicholson and Shane from the original work, where you plot the delta E peak in millivolts as a function of this variable, where this is sweep rate and this is Ks. And A is a collection of constants here. You'll notice that this profile will asymptotically hit basically what? 59, which is what you would anticipate for a reversible system. As the sweep rate gets faster, we're moving up that profile. Right? And so if you get a value, let's say here, right? You know what the sweep rate is because you're controlling it. So you know what that is. A is a bunch of constants. And so from that delta E peak, you can actually guesstimate the value of Ks. And that's extremely convenient, but you have to be extremely careful in your measurement. Why is that? Because this is the total delta E peak in your system. And for example, if you have a high solution resistance, your delta E peak will be bigger than 59 millivolts, not because the system is sluggish, but because you have a highly resistive environment. So you have to be extremely careful about that. Other ways of measuring Ks is to use so-called impedance measurements, which we will not really have time to discuss in this abbreviated version of the course. So then the question is, how do these voltammetric profiles change as variables such as the value of heterogeneous charge transfer kinetics as well as others? So here is a plot these profiles come from a program called DigiSim. So what we're presenting here is the voltammetric profiles as a function of Ks. So this guy here is fast Ks. And you can see that the profile looks very nice. The delta E peak, basically 59/n millivolts. As you make the process increasingly slow or more irreversible, then you eventually get to a profile that might look like that, where clearly delta E peak is ginormous. Notice also that the ratio of peak currents, I mean, you can eyeball it, but it should turn out to be 0.78, which is the value that the you wouldn't have when we discuss that one, okay? And so the ratio of those two peak currents, approximately 0.78. Compare these profiles to those profiles. These are profiles for a system that is electrochemically reversible, but we have increasing resistance in the solvent, in the solution. And you might say, they look very similar, and they do, but you can actually tell the difference, because if you look at this profile, you can almost think of it as rotating that entire profile across that line. If you move it that way or you move it that way, those two things will converge. And that is typical of a system that has large ohmic drops or high solution resistance. This brings, briefly into focus the importance of cell design and electrode placement. We will not be talking about cell designs, but in an electrochemical system, the way the circuit works is that you have a working electrode, which is located at quote-unquote virtual ground, an auxiliary or counter electrode that supplies whatever current and voltage you need to maintain the difference between the working and your reference electrode fixed. If you have a highly resistive environment, then the distance between your reference and your working electrode, the accompanying resistance associated with that distance, will be reflected in the cyclic voltammetric profile. And that will add an additional delta E to your delta E peak that has nothing to do with slow kinetics and everything to do with the resistance of your environment. This is sort of diagrammatically presented here. So depending on where you locate your reference electrode, whether you look at it here or here or here, that potential drop is going to get bigger or smaller. There is a limit, but you cannot have your working and reference electrodes in contact because that's a short. And so even when you have very careful placement of your working and your reference, there will always be a small distance between those two. And the resistance associated with that distance is called the uncompensated resistance. There are ways to compensate for that, usually using something called positive feedback, but you have to be very, very careful how you do that. Okay, for those who have interest, we can discuss that offline. Suffice it to say that especially in organic media where you have a highly resistive electrolyte, you have to pay particularly close attention to the interpretation of delta E peak values to make sure that in fact reflects slow kinetics and does not reflect slow charge transfer kinetics. The other thing that one can look at here, okay, so this is obviously the peak potential. If we draw a line through here, all right, and do that, we have basically that profile, right? Does that look familiar? This is what we saw from chronoamperometry, right? This shape is exactly that shape. Why is that? Remember the conditions in chronoamp, right? If this was the voltammetric wave, this was initial, boom, this is final. Complete concentration polarization, we look at the transient. This point also represents complete concentration polarization. You have the maximum current. And so the decay in that profile basically reflects the same dynamics as in chronoamperometry. And in the lingo of electrochemistry, people talk about quote unquote diffusional tails in the voltammetric profiles. And you can see them in all of them because they arise for the exact same reason. You reach complete concentration polarization. And so now basically that decay in the current is limited by the diffusion process. Now, if we look at the Randel-Sevcik, right, it tells you that the current is proportional to the square root of sweep rate. And you say, great. If I have a dilute solution, I mean, if this is low, all I have to do is scan fast enough and I'm good to go. Right? Again, let's take a vote. How many of you think that that's the case? Put 1 if you think yes, and 2 if you think it's no in the question and answers. See how many people we get. So we have 3 votes so far, 2s. We have a 1. a 2, another 2. I guess 2 is winning the day. A couple ones, okay? So let's go over this. Clearly, the peak current will increase as the square root of sweep rate, right? But you might remember this pesky little thing called the double layer charge or double layer current. You might remember when we talked about double layer current, that the double layer current is proportional directly to sweep rate. And so now we have an issue. Surely the peak current will increase with the rate as we increase the sweep rate at a rate of v to the 1/2, but the double layer is increasing linearly with sweep rate. And so the fact remains that as you scan faster and faster, your background is growing faster than your Faraday current. And so your signal to noise is degrading as you go to higher and higher sweep rates. And that's a limitation of cyclic voltammetry, because as we'll see in a few minutes, the most important variable you have in cyclic voltammetry is the sweep rate. However, when you change the sweep rate, you change your double layer charging current. So you have a changing background as you increase the sweep rate. And that turns out to be a colossal pain in the rear to try to accommodate that for. Okay. And so this is being depicted here. So here we have a series of cyclic voltammetric profiles. So here is a unit of 1, as you can see here. So here the sweep rate is A. Okay. Now we go to 9A. And you say, that's a peculiar number. Why 9A? (9A) because even I can take the square root of 9. That would be 3, right? And so what that means is that your Faraday current increased by a factor of 3, but your background current increased by a factor of 9. If you go to 100, now your peak current is 10, right? It's the square root of 100 times 1. Your background current has increased by 100x. If you go to 900, your current has increased by a factor of 30. Your background has increased by a factor of 900. The message here is that you have to be, you can certainly play around with sweep rate, but you have to be very careful that you're minimizing the contribution from double layers and IR drops, etc. And so, as I've mentioned previously, one of the real issues of cyclic voltammetry, even though it's very convenient, let me not underscore that, but the observed response is a convolution of a lot of stuff. There's a lot of moving parts here. And in particular, as you go to faster and faster sweep rates, things get increasingly more complicated. What about multiple electron transfers? And here we have to make a distinction between no interactions between groups. Whoops. There is a statistical factor involved. And that turns out to be given by this expression, where this is the total number of electron transfer minus the first equals 2RT over F ln of K. Let's say if you have a system with two electrons that can transfer 2 electrons, that delta E value is minus 35.6 millivolts for 2 1-electron transfers. Delta E0 values, right, this guy, that are more positive than this represent positive interactions. Values that are more negative than that represent negative or repulsive interactions. And what do I mean by that? An analogous thing is in polyprotic acids. You might remember when you talk, I don't know, probably sophomore analytical or something. So if you have, let's say, a dicarboxylic acid, right? You have a pK associated, let's call this one and this two. There's a pK associated with this one, there's a pK associated with that one. But even though they might be, way disconnected, if the connection is far enough so that there are 0 interactions between them, there is a statistical factor, meaning the fully protonated can be deprotonated here or here. The fully deprotonated can be, protonated in either one. Intermediate cases, you don't have that choice, because if you're going from singly ionized to doubly ionized, then you have less of a statistical factor. And that's what this basically statistical mechanics apply to multi or polyprotic acids as well as multiple electron transfers. The counter to that is if there's strong coupling, then the oxidation of one redox couple can dramatically affect the other couple. Meaning, if there's no interactions, you'll see a simple wave. As you start making that interaction stronger by having differences in E1/2, then you can have dramatic differences in the voltammetric profiles. So here we have ER. So you have a system that can exchange 2 electrons reversibly, depending on the difference in delta E0 prime. We start with a simple case. So you have very big difference between those 2 formal potentials. And so you see basically 2 1-electron processes. As that difference gets smaller, those 2 couples get closer to each other, a bit compressed. At minus 35.6, haven't you seen that one before? Right? Right there. If you were to look at that, I can assure you that you would not be able to tell me that that's a 2-electron process. As you go further in, meaning that the second electron is easier than the first, then you get a single wave that gets increasingly sharp. And so this delta E peak here, oops, is less than 59 millivolts, as will be the case here. And you have then multiple electron transfers. You can see that maybe it's a bit crowded here, but you can see what I'm talking about. So here we have when they're really separated. And then as you start converging, then eventually you get to something that is extremely sharp. Right? Because now you have a two-electron transfer. Remember that the height is proportional to n to the 3/2. So if you think of this as one electron, if these two electrons are basically much higher than just twice that. And then correspondingly, the delta E peak should be 59 over n. If it's two electrons, then it'll be 30 millivolts. Okay. That will become important when you have systems that can have interactions across bridging ligands that can make, let's say in the case of a multimetallic system, that can make or enable communication between those two discrete redox sites. And so when you oxidize one, the other one feels it and it's displaced in potential. And this becomes apparent when you have highly interacting multi-electron transfers, as you have in some systems that you design to be multi-electron. The counter to that, is that very often one would like to have multiple electron transfers because most chemical transformations involve the transfer of more than one electron. But if they are highly interacting, then that means that the potentials will be split and you sort of lose the advantage of having a multiple electron process. And so the idea is to have molecules that are capable of multi-electron transfers where there's essentially no communication between those redox couples. In those cases, what you will have is a voltammetric profile that has the amplitude of two electrons, but the shape of one electron. And so you begin to see how the voltammetric profiles and shapes can provide you with enormous information as to what the attendant electrochemical processes are. It's 5 before the hour. This is a good point to stop. Any questions at this stage? Let me look at see if any people have any questions. Does it matter how close the counter electrode is to the working and reference? You also want it closer because it mitigates, IR drops, but the more critical one is the working to the reference. What the counter can do is can basically control what your current distribution is. And if you're concerned with that, then closer or surrounding the working is a better situation. Let's see what other one. Does the surface area of this is the ring disk of the ring? Does the surface area of the ring much lower than the disk? And it is the ring disk electrode. The surface area of the ring is typically much smaller than the disk. After all, it's just a thin ring. What I didn't mention here that perhaps I should mention is that because it's dimensionally thinner, mass transport to the ring is faster than mass transport to the disk. So if you take two electrodes of equal total area, one a disk and one a ring, the flux at the ring will be higher than at the disk. Let's see. Those are all the questions. Any more questions before we log off for the day? You have 3 minutes to exercise your right to questions. I don't know if I mentioned this the very first day, but a number of you asked if there was a charge for this course, and obviously there isn't. Doesn't mean it's free. By that I mean, in the next few weeks, somebody will ask you for your help. Give that person some help and consider that the payment for the course. If there's no other comments, we will see you tomorrow. Have a great day.